body needs to regulate you. So we want to, my goal over the next couple days is to talk about how the heart generates this pressure gradient and how is it modified. How sometimes do we increase the pressure gradient under certain circumstances, like a sympathetic response, and how do we decrease it under other cases, like a parasympathetic response. And then we want to look at vessel diameter changes. How do we cause vasoconstriction, and under what conditions would we want to cause vasoconstriction to increase the resistance, and why would we want to cause vasodilation to decrease the resistance. So that's kind of the role we want to get at, or what we want to look at. So to do that, we're going to talk a little bit about the cardiac cycle. Then I want to talk about, I'm going to do this in reverse order, I think, from what I normally do it, just to be, because I feel like doing something different today. And I think it might be in a different order from the textbook or something, I really can't remember. Okay. I brought my book in here just to kind of ground myself, but I love talking about this stuff, so I have a tendency to get a little bit tangential sometimes. But so we'll do that. So we'll review the cardiac cycle. I want to talk about what cardiac output is. Okay. Cardiac output is simply defined, it's actually a measure of the efficiency of the heart. It's defined as the volume of blood the heart can pump in a second. And what's interesting to let you know this is that in 1 minute, and we'll see how this gets to, at rest while you're sitting there, in 1 minute, your left ventricle or your right ventricle, either one, pumps your entire volume of blood in a single minute at rest. Okay. That's pretty crazy if you ask me. So you got about 5 liters of blood in your body, and your little left ventricle can turn that pump all of that in a single minute. And that's at rest. Guess what that number can go up to when you start running around the track? That number can go up to, once every 15 seconds or so. It can pump your entire blood volume. And somebody who's freaky weird like Lance Armstrong, even before his illegal, substance enhancing abuse days, his cardiac output was in the neighborhood of 30 liters per minute. Which means that about every 5 to 6 seconds, his heart turns over his entire blood volume. No, that's not normal. Okay. But world-class athletes have incredible cardiac outputs. Anyhow, we'll look at that. And then to show you that what happens at the cellular level to generate this force and this pressure, we're going to have to talk about things at the cellular level. So we talked about contractions of skeletal muscle and smooth muscle. We talked about excitation, contraction, coupling in skeletal muscle and smooth muscle. Now we need to talk about excitation, contraction, coupling in cardiac muscle tissue. And we'll see that it's kind of a combination of the two types. So we're going to see some things that are really similar to skeletal muscle because it is striated and has troponin and has tropomyosin. And then we're going to see some things about it that are really similar to smooth muscle because guess what? It has calcium channels on the sarcolemma, and we see some calcium coming in from the extracellular. So it's kind of a merger between the two. And then we'll also see that there are some cells in the heart that don't contract. They're muscle cells, but they don't contract. And they're in, if you remember from anatomy, we talked about this region called the SA node and the AV node in terms of being able to generate signals. They function kind of like neurons in generating action potential. So we'll want to talk about those cells as well. They're called autorhythmic cells. So we'll end with a discussion about that. Is that okay? You guys good with that?